Kinesthesia and proprioception are both terms used to understand perceptual development, although the term kinesthesia can place a greater emphasis on motion. Proprioception, from Latin proprius, means one's own, and perception is the sense of the relative position of neighboring parts of the body and strength of effort being employed in movement. It is distinguished from stereoception, for example, by which we perceive the outside world, and interoception, by which we perceive pain, hunger, and the movement of our internal organs. The position movement sensation was originally described in 1557 by Julius Caesar as a sense of locomotion. And much later, in 1826, Charles Bell expanded the idea of muscle sense, and this is credited with the being of one of the first described physiological feedback mechanisms. Bell's idea was that commands are carried from the brain to the muscles, and that reports on the muscle's condition would be set in the reverse direction as a feedback process. Later, in 1880, Henry Charton suggested that the use of the term kinesthesia instead of muscle sense of the basis that some afferent information was coming from other structures including tendons, joints, and skin. In 1889, Alfred Goldscheider suggested the classification of kinesthesia into three different types: muscle, tendon, and articular sensitivity. But only in 1986, Charles Scott Sherrington published a landmark work that introduced the terms proprioception, interoception, and stereoception. The stereoreceptors are the organs responsible for information from outside the body, such as our eyes, our ears, our mouth, or even our skin. The interoceptors then give information about the internal organs, while proprioception is our awareness of movement derived by muscular tendon and articular source. Such a system of classification has kept physiologists and anatomists searching for specialized nerve endings that transmit data on joint capsule and muscle tendon. But how do we sense our body movements? How does the brain process information or data from joint capsules and muscle tension? To answer these questions, let's start by defining what is proprioception and by looking into the structures located in our body that provide proprioceptive information to the brain. Proprioception refers to sensation from the musculoskeletal system like muscles, tendons, joint capsules, and ligaments. They are constantly determining the body position and the way it's moving through the space. Changes in tension, sensations of stretch, and muscle response provide information to the brain that determines whether the body is walking, sitting, standing, running, or dancing. Proprioceptors allow the mind to understand the body without visual aid. Axial potentials reach the cerebellum and transmit into this information. This information is then used to fine-tune the body's response, such as initiate muscle contractions to enhance speed. This creates a stronger sense of coordination in the movements of our body. They are very low threshold mechanoreceptors that inform the central nervous system about joint movement by detecting the stretching of the tissue in which they lie. There are several types of proprioceptors. Let's start by reviewing some of them. Muscle spindles, for example, are located in the muscles. Golgi tendon organs, or also known as GTO, are located in the muscle tendon joints. And joint receptors are located in the joint capsule and ligaments. Let's begin by talking about the muscle spindles. The muscle spindles run in parallel to the regular or extrafusible muscle fibers, and they are cigar-shaped or fusiform structures called muscle spindles. They are sensory receptors which the belly of a muscle which primarily detects change in the length of the muscle, and they convey length information to the central nervous system via sensory neurons. The information can be processed by the brain to determine the position of our body parts. The response of muscle spindles to change in length also play an important role in regulating the contraction of muscles and the sensory motor development. The density of the muscle spindles vary from muscle to muscle. Muscles used for precise movements like the extraocular eye muscles and intrinsic muscles of the hand and small muscles in the neck have a higher density of spindles. Muscle spindle primarily detects change in the length of the muscles. They play again an important role in regulating the contraction of muscles by activating motor neurons via the stretch reflex to resist muscle stretch. The Golgi tendon organs, also known as GTO, is located at the insertion of the skeletal muscle fibers into the tendon of a skeletal muscle. They lie into the myotendinous junction. The GTO consists of a slow-adapting sensory nerve fiber embedded within the collagen of the tendon. They are very sensitive to stretching and inform the central nervous system about the tension in our muscle. The GTO signals the central nervous system the tension developed by the muscle during contraction or stretch. For many years, it was thought that these receptors had high thresholds to muscle tension and participated in controlling muscle activity only at extreme tension, functioning as a protective device. But actually, the tension organs are relatively insensitive to tension when they apply to the muscle by stretching, but they are extremely sensitive to tension developed by the muscle when it contracts. The reason for this is that the tension on tendon organs is different under passive and active conditions. But what is the difference between the GTO and the muscle spindles? That's a very interesting question. They are both muscle receptors, but the muscle spindles and the GTO are a little bit different because they respond differently to passive muscle stretch and active muscle contraction. Both afferents discharge in response to passively stretching the muscle, although the GTO discharge in much less than the muscle spindle. We also have the joint receptors. Joint receptors are found in the synovial junctions between bones. The receptors detect mechanical deformation within the capsule and ligaments. They serve to two main purposes: to protect the joint from potentially injurious flexion and extension, and serve as proprioceptors. There are four types of sensory endings that make up joint receptors: free nerve endings, Golgi-type endings, Ruffini endings, and passiniform endings. Until recently, it was commonly believed that joint receptors fired only at the extremes of movement. However, now we know that it has been proven that there is always some amount of receptors firing at any given point in range of motion of a certain joint. Free nerve ending is located in both the fibrous capsules and ligaments, and they signal tissue damage. Golgi-type endings are slow-adapting receptors that are basically resemble the tendon organ and is found only in ligament. Its functional role is still unclear. It has suggested that they possibly play a protective role for the joint. Ruffini-like receptors are slow-adapting nerve fibers located in the fibrous part of the joint capsule. They signal static joint position, joint movement, direction, and speed of movement. They are very important joint receptors. Passiniform receptors are rapidly adapting nerve fibers located in the fibrous parts of the joint as well, but they signal joint movement, particularly movement velocity. Another type of receptors that we have in our body system are called cutaneous receptors. The skin contains numerous sensory receptors which receive information from the outside of the environment, so they are considered to be esteroceptors. Cutaneous receptors are sensory receptors located in the dermis, which is a layer of our skin. These receptors are responsible for the sensations of touch, pressure, heat, cold, and pain. They are classified as mechanoreceptors, which are associated with pressure, thermoreceptors, which are associated with temperature, and nociceptors, which are associated with pain. Basic modalities include again touch, pressure, heat, cold, and pain. This may be evoked by stimuli single receptor type. Sensations such as itch, tickle, dampness, texture, and firmness may be evoked by stimulating a single receptor type. However, it's most likely that simultaneous stimulation of many receptors in the skin and deeper tissues may provide a fusion of information to the brain. Finally, we have the vestibular system, which contributes to balance and to the sense of spatial orientation, and the sensory system that provides the leading contribution about the movement and our sense of balance. Together with the cochlea, a part of the auditory system, the vestibular system constitutes the labyrinth of the inner ear. As our movements consist of rotations and translations, the vestibular system comprises of two components: the semicircular canal, which indicates rotational movements, and the othelids, which indicate linear acceleration. The three semicircular canals are arranged perpendicular to each other. This allows the semicircular canals to inform the central nervous system about all possible angular or rotational head movements. Specifically, the endolymph in the semicircular canal displays the cupula, which causes the hair cells within the canals to bend. The hair cells are either excited or inhibited, depending on the direction of the bend. The otolith organs are made by the sacral and utricle. They are sensitive to gravity and linear acceleration. Because of the orientation in the head, the utricle is sensitive to a change in horizontal movements, and the sacrus gives us information about vertical acceleration, such as we are inside an elevator, for example. Like the semicircular canals, the utricle and sacrus contain hair cells embedded in a jelly-like substance. In addition to jelly, contains small calcium carbonate crystals called otoconia. The otoconia have a higher specific weight, which allows them to be influenced by gravity. In summary, the vestibular system sends signals primarily to the neural structures that control our eye movements and to the muscles that keep us upright. The projections to the muscle provide the anatomical basis of the vestibulo-ocular reflex, which is required for clear vision. And the projections to the muscles that control our posture are necessary to keep us upright. From a developmental perspective, we should keep in mind that our proprioceptors developed very early during the early stages in our lives. From a developmental perspective, we should keep in mind that our proprioceptors developed very early during the gestational period. The best evidence of this early development are the infantile reflexes, which are stimulated through kinesthetic receptors. The onset of a reflex indicates that the corresponding kinesthetic receptor is just functional. The vestibular system, for example, develops concurrent with the auditory system. Our vestibular receptors are adult-like by about 14 weeks of gestation, and at birth, the vestibular system is mature. With fully developed structures, hair cells are functional, and the 8th cranial nerve is myelinated to adult level. So to finish here, putting all these receptors together, we have what we call kinesthetic sensation. What is important to remember here is that although differences in location and sensitivity to different forms of stimulation exist, all receptors work together in controlling the activity of the muscles and body systems with which they are associated. The function of our kinesthetic receptor is critical for motor skill performance because it yields information about the relative position of the body parts to each other, the position of the body in space, and the body's movements and the nature of objects that the body comes into contact with. The development of the kinesthetic system has many functionalities. For example, tactile localization, which is our ability to identify without looking the exact point on the body where the tactile stimulus is applied. Another example is perception of body or body awareness, which includes laterality and lateral dominance in perception of our limb movements. We also have spatial orientation and directionality. That is our perception of our body's location in space and the ability to project the body's spatial dimensions into surrounding space. And this is independent of vision. Although directionality is often linked to laterality, an awareness of the body's two distinct sides, left and right, children with a poor sense of laterality also have poor directionality. Although this relationship seems intuitive, logical, deficiencies in laterality are not known to be the cause of deficiencies in directionality. Well, we hope by now you have a clear idea about what causes our kinesthetic sensation, what are the structures involved in our somatosensation, and how these structures are developed across lifespan.